Okay, in this question, we're going to go over AP Calculus AB FRQ number 2 from the 2007 exam. And so in this question, they give us the rate at which people enter an auditorium. And so we always need to be super careful in these questions. We're saying, okay, this is the rate, and this is the function. This is already the rate at which people enter the auditorium. And that's measured in people per hour. No one in the auditorium at time t equals 0. Doors close when the concert begins at time t equals 2. So how many people are in the auditorium when the concert begins? So no one's there at time t equals 0, and they've only got 2 hours. And this is the rate at which they go in. Well, if you have the rate at which people enter, or water flows in, or the rate of anything, and then you want to know the total amount of change of that stuff, the net change it's often called, we just integrate. So this is a fairly straightforward one. For part A, just the integral from 0 to 2 of r of t dt. 2. This is a calculator allowed question. So that's actually just 980. And that's not a terrible definite integral to take by hand. Just power rule, but calculator is allowed, so go for it. Find the time when the rate at which people enter the auditorium is a maximum for part B. Well, if I want to know when something is a maximum, I need to take the derivative of that thing, set it equal to 0, and see, where does that change from an increasing rate of change to a decreasing rate of change. And I might potentially need to consider endpoints if I have a closed interval, which I do have a closed interval here from 0 to 2. So the thing that I want the maximum of is r of t, the rate at which people enter the auditorium. So I need to take the derivative of that. And many times people are saying, wait, isn't it already a derivative? It's a rate? Yes, it is already a derivative. That's why we took the antiderivative in part B. But now, because I want to know the maximum of that rate, I need to know the derivative of that. Think about it as if I wanted to know when acceleration was maximum, I'd have to take the derivative of acceleration and set that equal to 0. Whatever you're finding the maximum or minimum of, you need the derivative of that thing. So r prime of t is a little power rule here. 2760t minus 2025 t squared if you do your power rule. Set that equal to 0, and you're going to get two different solutions. You're going to get t equals 0, of course, and then you're also going to get 1.36296. And again, that's just by setting that equal to 0. Now, because this is a closed interval, as we said, it's also possible that my maximum could occur at the endpoints, which are 0 and 2. Now, fortunately, one of those endpoints is actually one of your critical numbers, so it showed up twice. Little check for you there in case you forget. But we do need to remember to consider t equals 2 as well. So if we're thinking about this, this situation, one option is to simply plug in and figure out what is r of 0, what is r of 1.36296, and what is r of 2. Whichever of those three is the biggest is your maximum rate, because those are the only places your maximum can occur. Now, I actually can do a little better than that in this case, I think, because the derivative here is a downward facing parabola. The sign in front of the t squared term is negative. It's a downward facing parabola. I know what this graph looks like. It looks something like this. Excuse my squiggly parabola there. So it's this second x-intercept over here where the derivative changes from a positive derivative to a negative derivative. And in order to be a maximum, you have to have that happen. Now you say, well, what about the endpoint? Well, look what happens at this x-intercept. The rate is now decreasing because r prime is negative. So you're not, r of 2 can't be bigger than r of 1.36296. So that one's got to be my maximum. So the question asks the time at a maximum. So we can just say it is this one. That's our max. And it says to justify. And so again, one justification would be to just list these three different R values, the outputs of these things, and say well, that one's the biggest. The other is to say that at 1.36296, R prime changes from a positive to a negative, meaning that R changes from increasing to decreasing, and then it decreases all the way until 2. Okay. Part C, what's the total wait time? Now this question is a weird one for me because they have this kind of description here. The total wait time for all people in the auditorium is found by adding the time each person waits, starting at the time the person enters the auditorium and ending when the concert begins. That really is more or less useless, in my opinion, for this problem. And usually I feel like the College Board does not give me information that I don't need. But here, I don't really care about that. It's just that the function W models the total wait time. How are we calculating W? I don't really care. W is the total wait time. The derivative of W is this. Find W of t minus W of 1. Well, this is a lovely story about total wait time, but all I need to know is that I have W prime and I need W, which means I need an antiderivative. And I want, in particular, W of 2 minus W of 1. Well, if I take the antiderivative of W prime, part C here, if we take the antiderivative from 1 to 2 of W prime of t, when you take an antiderivative, you get the original function, and then you plug in the endpoints. So you get the antiderivative, W of t, have your endpoints, plug them in, and you get W of 2 minus W of 1. And so because this is a calculator allowed question, I can just take this expression and take what I know about W prime, 2 minus t times R of t, which again I have R of t, and just plug that whole thing in my calculator and get the answer. When I do that, I believe what I get is 387.5. And they don't ask me to justify or explain or anything like that. So I think exactly what we write here is all that we need to show. On average, how long does a person wait in the auditorium for the concert to begin? Well, we kind of have to put a couple things together to do this part D here. And if we think about what they're asking us here, on average, how long does a person wait? Well, we could use the average value formula and think about it that way in terms of definite integrals, but I think in this case it's easier just to think about it in terms of average. And here's where maybe the explanation for part C is a little bit helpful, because W of t represents the total wait time. So if we found W of 2, that would be the total wait time for everybody. And then if we just divided that by the number of people that are in the auditorium, well, that would be the total wait time, W of 2, total wait time, divided by the number of people. Well, the number of people, we found that in part A. That's 980. So we just take this W of 2 and divide it by 980. Well, how do we find W of 2? Well, W of 2 should be just the definite integral from, it should be the definite integral from 0 to 2 of w prime of t plus how many people were waiting in line at the beginning, because this definite integral represents how much that has changed here, or plus the total number of people who are waiting in line to start. But there is no initial condition here because nobody was in line and they can't have been waiting before it started. So we just plug into our calculator the expression for w prime of t and do our math 9, our definite integral, just like we did up here. But here in part D, it's from 0 to 2, not 1 to 2 like it was in part C. When we do that, I believe we get 760. Take that 760 and divide it by 2. Let's see if we can give ourselves a little more room here. Oops. Go down here. Take that 760 divided by 2. 760. Sorry, I said twice there, divided by 2. We're finding w of 2, which is 760, but we're not dividing by 2, we're dividing by 980 because that's the number of people. Because the 760 represents the total number of minutes that all the people waited. 980 represents the total number of people. So minutes divided by people should give us our average, which is 0.7755. Okay, so that is 2007 FRQ number 2.